Hey, good morning. Good morning, welcome to class. So today we're going to continue talking about camera models and in particular calibration and measuring things in scenes using our knowledge of geometry. So it's kind of, it's going to cement some of the things that we talked about in the last class. So remember that last class we talked about the pinhole camera model, which is a very basic model that everybody should know. So you start with a point, you have a point in a 3D scene, which is denoted x, y, z. In this class, we consider z to be the camera axis, which is consistent with Hartley and Zisserman. And then y we usually think of as the vertical axis or the gravity direction, and x is the direction that's perpendicular to both of those. Then the point is shooting a ray through the camera center, and then it hits the image plane at some point. So if it hits within the CCD area, then you're going to measure some light from that point. And we can compute the position where the 3D point hits the image plane based on the focal length and the principal point. So if our camera is in world coordinates, then the equation is just u equals fx over y plus u naught, and u equals fx over z plus u naught, and v equals fy over z plus v naught. And we can write that as a homogeneous system of linear equations. So just as a simple exercise, I want to go through how we can compute, if we know, let me write down the camera matrix, and then look at how we can compute the camera's position in the world from it. So under this model, we have some 3D point x, y, z, and it undergoes some rotation and translation. So rotation is a 3×3 vector, and translation is a 3×1 vector. And that maps, x, y, z 1. So the 1 is so that we can add a translation. So this makes it so that we have r times x, y, z plus t. And that maps from the world coordinate system into the camera's coordinate system. Then that gets projected down. This together is multiplied by some k, which is typically ff u naught v naught 1, which maps the point to homogeneous coordinates. Whoops, uv w1. Okay. So k maps it from the 3D point in the camera coordinate system down to somewhere on the image plane. So one thing we could do is we can look to see, so what is, if we know r and t, then how do we figure out what is the camera's position in world coordinates? Because r and t basically maps maps a world point into the camera's coordinate system. So what if we want to map the camera's coordinates into the world coordinate system? For example, if we want to say, what is the position of the camera and what is the direction that the camera is facing in our world coordinates? Then we can do that by saying that we have xc, yc, zc. So this is x, y, and c in the camera's coordinate system is equal to r times xw, yw, zw plus t. So r and t are mapping from the world coordinates to the camera coordinate system. So if we map the camera itself onto, or what will be, so if we map the, what am I trying to say? So how do we solve for the camera's coordinates given or how do we solve for the camera's coordinates given this? So what will be the camera's coordinates after we map into the camera's coordinate system? Right, 0, 0, 0. So after we map into the camera's coordinates, then xc, yc, zc, the camera should be at 0, 0, 0. So we just want to solve for we want to see what is the value of xw, yw, zw, and that will give us the camera's coordinates in world coordinates. I mean, the camera's position in world coordinates. So if we say 0, 0, 0 equals r xw, yw, zw plus t, then we get xw, yw, zw equals r inverse equals negative r inverse t, right? So this is the camera's center. So the camera center equals negative r inverse t. So I just pulled the t over to this side and then multiplied both sides by r inverse. And then the camera so what's the camera rotation? So if I'm rotating the point by r to get from the world coordinate system into the camera's coordinate system, then what is the rotation that would give me, what is the rotation of the camera with respect to the world? So if I'm mapping from the camera coordinate system to the world coordinate system, what's my rotation? So the statement was negative of the world camera rotation. I guess it's better to say the inverse of the camera, right? So the camera rotation is just R transpose or R inverse. Note that R inverse is equal to R transpose. Okay. So the camera's so the camera position in the camera's pose in world coordinates is just negative r transpose t, and the camera's orientation in world coordinates is just r transpose. So if you do like structure for motion, a lot of times you'll represent the camera or at least if you like plot cameras, you'll want to represent it in the world coordinates, not represent it in terms of r and t, because then you're representing kind of the mapping into each camera's coordinate individually. Okay, so that was working from this. So this is the full projection matrix. And note that even though in the full intrinsic matrix we have a scale or skew and aspect, skew is almost always assumed to be 0, and I would usually assume that aspect is 1, even though sometimes people do solve for the full intrinsic matrix. So we're going to show for some ways to solve for these parameters given different kinds of scene information. And then also to review, we talked about vanishing points, which are going to be important today. So remember that a set of lines that are parallel in 3D will intersect at some vanishing point. If two sets of lines are parallel to the same plane, then they'll each intersect at some vanishing point that's on the vanishing line of that plane. If you had a whole bunch of 3D planes that are parallel, then they'll intersect in the image plane at that vanishing line. And so, and it's possible to have, if the lines are parallel to the image plane, then they'll intersect at infinity. But we can still represent that intersection in homogeneous coordinates as some uv0. So this class we're going to talk about how do we calibrate the camera. So how do we solve for K, the intrinsic matrix, and the extrinsic matrix, RT. How do we measure the size of objects in the world from an image? And then also talk about some of the other properties of the camera, like focal length, field of view, depth of field, and how they affect the imaging. So there's actually a couple of main ways that we deal with measuring size and calibration. We can do it purely through the vanishing point kind of reasoning, or we can do it more algebraically through the projection matrix. So one way that we can calibrate, so we can view calibration as just a problem of solving for KRT together. So we could solve for this as some 3x4 matrix in homogeneous coordinates. So there's 11 free parameters. And one way that we can do that is using some object where we know the 3D points, and we also have marked or have detected the 2D points, so like a calibration grid. So for example, you'd have, you can set up something like this. You can say that this coordinate is 0, 0, 0. You can detect all the 3D points automatically, easily with like a Harris corner detector or something. Then you would say, because it's on a grid, you know the 3D position of each of these points compared to your origin. And so now you have a set of 2D and 3D correspondences. So for each point that you detect, you know a U and a V, and you know the X, Y, Z. So how many constraints does each 2D, 3D match give us? For every point where we know a 3D value, how many equations do we get from that? Yeah, so there's 3. So I asked because it's something that's kind of easy to get a little deceived by. So there's 3 equations, but also note that this W is a variable that is an unknown as well. So even though it looks like we've got 3 equations there, there's only 2 constraints. So really, we just have a constraint. And another way to think about it is that you've got some. Well, we've just got a mapping onto U and V that are known. So we have constraints for U and V, and then W is something that we have to solve for in the process of creating these constraints. Another way to think about it is if I were trying to, let's say that I instead knew M, and I knew X, Y, and I knew U and V, but I didn't know X, Y, Z. So then there's going to be like one thing that I don't know, right? There's going to be one parameter to X, Y, Z that I don't know, which is W. And that's basically how far along the ray through, if I project a ray from UV through the camera center, how far along that ray that 3D point is. Okay, so one way that we can solve this is just using linear least squares. This is certainly the simplest thing to describe. So I've got my equations here. If I just multiply them out, I'll get WU equals M1, where M1 is the top row, times XYZ1, and W equals M3 times XYZ1. And then if I just substitute M3 XYZ1 for W, then I get constraints of this form. So it's always easy. I mean, many of you are probably experienced with this, but even if you're not as accustomed to solving systems of linear equations, the first thing to do is just write out the equation, and then remember what your variables are, and put them in a big column, and then write your coefficients so that when you multiply your coefficients by your variables, you get the same thing that you wrote for your equation. So you can, this same equation, this is the starting point. If you want to try to solve, if you want to do triangulation, so given two cameras, solve for x, y, and z, you would use this equation as well. But then you would end up with a different, you'd end up with x, y, z on the right side instead of all the m's. So, yeah. So in this case, we end up with something of this form where we've got it in the homogeneous system of linear equations forms. So it's pretty easy to solve. We need at least 6 points, at least 5.5 points anyway. So 6 points and then at least a u or a v value for some point. And this is often used as an initialization for nonlinear methods. One disadvantage is that it doesn't directly give you the camera param. Oh, question? Is W what?
The same to 6 points?
No, W is not the same. So actually, notice here, this is something that I kind of glossed over, but it's an important thing to point out. The way that I get these coefficients is that I do WU equals M1X and W equals M3X, where by X now I mean the full point. And then I'm substituting M3X for W. So there's no W's in here. Right? So I've explicitly solved for W, or I've substituted for W so that I'm not solving for W as part of this system. But W can be different for every point if I were doing like the projection onto UV. Okay, so it's easy to formulate and solve. This often is used to provide initialization for nonlinear methods. A downside is it doesn't directly give you the camera parameters, but you can do a QR decomposition, taking advantage of that K is an upper right triangular matrix and R is an orthonormal matrix, to decompose your parameters into K, R, and T. It's actually, there's some tricky bits to it because you end up with 4 possible different solutions that correspond to like whether points are behind the camera or in front of the camera, so you have to do some checks. Because mathematically you could project a point onto the plane from behind the camera, or you could project it onto the plane from in front of the camera. And so you need to make sure that you are doing it, that you've got your ordering the direction of the camera correctly, so it's facing forward, not backward. But anyway, it's not super complicated, but it's just a little tricky. So this link, which I'll let you go to on your own if you're interested, shows you how to decompose it. This also isn't modeling radial distortion, so you have to add more. That you have to do with a nonlinear system. And you can't easily impose constraints like a known focal length because you've just wrapped together your R, T, and K. And it doesn't minimize the projection error, because you're solving for some error in a homogeneous system rather than just minimizing. What the ideal thing to do is to minimize the squared distance of the pixel that you project to in Cartesian coordinates with the known value of that pixel. And we'll get into later a little bit, in a week or so, we'll talk more about why this homogeneous system of linear equations doesn't actually give you the least squares projection error. or minimize it. So the preferred solution is to do a nonlinear method. So you say that the error is the difference between the projected point and the known point. And here a projected point is just UV, not UVW. And then you can minimize the error using Newton's method or some other kind of nonlinear optimization. It's easier to say than to do if you're coding it. OK, so that's one method. So that method will give us, so with this method we get, we first get the projection matrix, and we can go through a little bit of math to decompose it into KR and a T. There's another method that's completely different, which is just using the vanishing points. So here we can solve for the camera rotation and the intrinsic matrix. All right, so how do the vanishing points help us? Well, so there's some, so we're going to, let's say that we're able to find three sets of vanishing points that, or three vanishing points that correspond to orthogonal directions. So this is really common, like in a city scene, there'll be lines that are vertical and then lines that go down in like two different directions, like the two sides of a building. And so if we can find these vanishing points, which sometimes you can do automatically, then that gives us some constraints. So when you're thinking about solving parameters, you have to think about, well, what are the actual things that I know, and then figure out how those relate to the parameters that you want to solve. So in this case, what we know is that we have 3 points that such that the 3D directions that project onto them are orthogonal, right? So there's a vertical direction and a direction this way, for example. Since they're orthogonal, what is the constraint between these 3D vectors? So I didn't hear. A couple people said something, but I didn't hear either one. Yes? Right, their inner product is 0. Or another way to write it, since they're another way to write it is that they're well, actually, this is just another way to write it. Same thing. Inner product is 0. So we can just use this one constraint to solve for k. So that might be a little bit surprising at first, because if you look at this, we've got a projection from our 3D point. We don't know the 3D direction. All we know is the vanishing point, which is the 2D direction. So little pi in this figure is the positions of the vanishing points. It's these positions in homogeneous coordinates, and this one. In order to solve for all 3 parameters, we need there to not be an infinite vanishing point, but let's just assume we have 3 finite vanishing points for now. Okay, so we've got p, which we don't know x, we don't know r, we don't know k, and we're going to solve for k. And if I assume that these vanishing points are in the vertical direction and in the x, if they're in the x, y, and z direction, then I can also solve for r. So how do we do that? So it's actually pretty straightforward. It's actually kind of surprisingly straightforward math, although I think it's really not an obvious that you can get that solution. Okay, so we have, for example, is this visible? Yep. Okay, so we have, for example, P1 equals KR big P1. So here, little p1 is one of the vanishing points in homogeneous coordinates, and big P1 is the 3D direction, which we don't know. We also don't know k and r, and for now, let's try to solve for k. Okay. Likewise, we have another one here, P2, it's KR big P2. And all we know is that P1 transpose P2 equals 0. If I wrote P2 transpose P1, I'd get the same thing. So it doesn't really matter what order I do that. And so now I can solve. So now I just need to solve for P1 and P2 and then substitute and see what happens. So this gives me that P1 equals R inverse K inverse little p1, and P2 is R inverse K inverse little p2. So these R's and K's are the same because it's the same image. And so this gives me that P1, little p1 transpose K inverse transpose. I'm using negative t as inverse transpose. Oops, sorry about that. Whoops. Sorry. Inverse transpose, R inverse transpose, R inverse, K inverse, P1 equals 0. Okay? So what is R inverse transpose? What's simplified R inverse transpose? R. Oh, yes, thank you. This should be P2. Yeah, so R inverse transpose is just R, and R inverse is identity. So this gives me P1 transpose, K inverse transpose, K inverse, P2 equals 0. And then I likewise have one for P1 and P3, and P2 and P3. I'm going to just put dot, dot, dot to indicate that the same K inverse transpose K inverse go there. These are all equal to 0. And then I have K equals FF U naught V naught 1. And K inverse equals 1 over F, 0, negative U naught over F, 0, 1 over F, negative V naught over F, 0, 0, 1. And so then I can just, if I plug in my K inverse into this equation, then I'll get a quadratic equation in terms of my parameters. But I have 3 equations, so it's not a linear system, but I have 3 equations and 3 unknowns, and so I can solve even symbolically for my parameters given these constraints. The equation is a little bit messy, though. It's pretty long, actually. So one thing, by the way, as an aside, if you want to, in your next homework, you'll need to at some point normalize your coordinates, which means that you want to compute K inverse times UV1, or you want to compute U and V after pre-multiplying by K inverse. And so to do that, you get, U normalized is equal to U minus U naught over F. And V normalized equals V minus V naught over F. So that maps a pixel from its original coordinates to its normalized coordinates, where it's normalized by the intrinsic matrix. You can figure that out yourself just by doing K inverse. But I've always done, in my code, I've always done K inverse and then divide by the third coordinate. But this is a lot simpler. Question? How would you get what? So these P's are just the 3 vanishing points.
As we saw that the vertical lines don't really mean.
Yeah, so I'll get to that. So this is a case. So let me get to that in just a second. In most images, if your image is not exactly vertical, then all 3, if it's not directly facing any of the major planes, then all 3 of these vanishing points will be finite, and then you can solve this completely. If one of your vanishing points is not finite, so in this case, where our image plane is aligned with the vertical direction, then what you can do is you can still solve for F, and then you're going, still showing you that. You can still, I was meant to be flipping back to here. So you can see here we have two finite vanishing points and one infinite one. If we had 3 finite, then this would all be fine. If we only have 2, then we can solve for f, and then we can, we'll get that u0 and v0 are along some line, and then we choose the closest point in that line to the image center. And then if we only have one vanishing point, which would be like if I'm staring straight down the street, and so one finite vanishing point, so that the vertical vanishing point is at infinity and the horizontal vanishing point is at infinity, then I would just assume that the principal point is at the center of the image and solve for f.
How do we define, is it any parallel lines meeting at a vanishing point, or they have to be perpendicular parallel lines which meet
So we have to find, for this case, the constraint that we're using is that we know these directions are perpendicular. So they have to be perpendicular to do it this way. If you knew that they were at like a 45-degree angle, then I think you could also create a constraint based on that. But it would, I would have to think about that. It would be more tricky.
You just have a cos 45 term there.
Yeah, the thing that's tricky is that the rotation, yeah, that would be fine, actually. Yeah, those directions, that's right, yeah. So you would just get a different...
Equal to 0, instead of equal to 0, we'll have equal to cos 45.
Right, yeah. So if they were not orthogonal, but they were just at some other angle, they can't be parallel, but if they're at some other angle, then you could just substitute the cosine of those relative angles with 0.
So the norm would come into play where r will not probably vanish. Is it because you'll have to divide it by the norm to get cos? Like, inner product divided by the norms of the two vectors?
I think r will still vanish because it's the capital P1 transpose, or it's the x transpose x would be equal to some constant, but the rest of it would be the same when I substitute for the x's. Okay, so now let's say, okay, so we've solved for k. Now can we solve for r? So here we need an additional set of facts, which is we're going to assume that these directions that we've found are in fact the x, y, and z directions. And often that's a practical thing to do because we can say the vertical vanishing point is the y direction and the other two directions we're going to set as our x and z directions. And then at least we have like some world coordinate system that kind of makes sense. So this one is really easy, by comparison anyway. So here we can just note that we find our first vanishing point, let's say a vanishing point in the x direction, and we set that x is equal to 1, 0, 0, 0. So let me I will actually do it and show you something on this. So take that out. So remember that the full equation is little pi is equal to k times rt and big pi. Okay, so now let's say that this big pi is going to be px. And so big px is the direction of the x vector in the world. And little px is the vanishing point of the x direction on the image. So in other words, big px is 1, 0, 0, 0. So that means that it's in the x direction at infinity. So I'm mapping a 3D point at infinity onto the image plane. And so this will just give me little px equals k. If I write this as Am I off the screen? Okay. So I can write, I'm going to write my R as 3 column vectors, which are Rx, Ry, and Rz. So each of these column vectors are actually a projection onto an axis. They're projecting onto the x-axis, the y-axis, and the z-axis. And so my big px is just, or my little px is just k times Rx, where Rx is a 3 by 1 vector. K we solved previously by assuming orthogonality, which of course will also be true if these are going in the x, y, and z directions. And I know my vanishing point, I know K, I just don't know R yet. P has 2 values, so this is going to give me some equation in terms of UW, VW, and W. So I've got 2 knowns for P and 3 unknowns for Rx, except that, remember that the length of Rx is equal to 1, right? So after I multiply this out, I'll get some Ux equals FR11 plus U naught times R13, and Vx equals F, FR12 plus V naught times R13, and W equals R13. Right, so I'm still going to have, oops, sorry, this is W times Ux, W times Vx, and W equals 113. Ux and Vx are known, F, U naught, and V naught are known, but I don't know R1, R2, R3. I can substitute in there, and then I'm going to still get some R1. I'm still going to only be able to get my R up to a scale. But since I know that my length of R is 1, my length of this Rx vector is 1, then I'm going to, maybe, sorry, let me just write this as Rx1, Rx2, Rx3 to clarify. So those are all part of the x vector. Since I know that the length of Rx is 1, then I normalize it so that the length is 1 in order to solve for the scale value. So that gives me the left side of the rotation matrix. I do the same thing for the center and the right side for to solve for the rest of the rotation matrix. Any questions? Yeah.
Could you show the previous paper that you
Yeah.
The one with the little piece of the
Uh-huh.
Here, how do we get K from little p1s and little p2s when there was W still as a variable? We knew only U and V in p1s, right?
So,
We should have lower part of that piece.
mm-hmm.
So K inverse has 3 variables, F, U naught, and V R, right?
Yeah, so you can substitute. So after you, so I didn't write out all the equations, but after you, so if you here you can multiply K inverse times P1, and then you take the transpose. But when you do that, then what it does is it transforms. You can solve for W so that you transform that UN is equal to U minus U naught over F, and Vn equals V minus V naught over F. And so you can still get rid of the W's by substitution like we did for the other equations. So yeah, so if you just take this, I think I don't want to, I don't want to like write it out right now. But if you just, if you multiply that out, then I think you'll see how you can can deal with it. Or I guess I would say just, yeah. So. Oh, sorry. Let me simplify that answer. Sorry, I did not give a good answer to that. Okay, so let me give the correct answer. So the question was, we don't know W, but actually we know W. So P1 is equal to U1 V11. So we actually know, in this case, we know the Cartesian coordinate. We know the position on the image plane. And so when we write that as homogeneous coordinates, we just write it as that position and append a 1 to it. So converting from Cartesian to homogeneous coordinates. The case where we have a free floater, when we have like a floating variable, is if we only know a position in homogeneous coordinates and we want to figure out the position in Cartesian coordinates, then we have some scale factor to deal with. But in this case, we have the position in Cartesian coordinates. We know the position on the image plane. So to write P1 in homogeneous coordinates, we just add a 1 to it. Okay, so we've looked at two ways to solve for the camera parameters. The one based on purely like a calibration grid where we solve a system of equations. The other where we use vanishing points to solve for the rotation and intrinsic matrix. With the latter one, we haven't solved for translation because that requires, we can still arbitrarily define our 3D position in the world. But if you have some object where you want to say that that's 0, then you can specify that if you want to say like some point on the ground is x equals 0, y equals 0, z equals 0, then we can also solve for the translation. You just need to know specify some scene point. Right, so now let's look at how we can measure 3D size of objects from an image. So I think this is a nice illustration that just because we automatically account for the perspective when we look at images. And so even like if you were to visually say like how big is the guy on the right versus the guy on the left in the image plane, I would tend to first think like maybe it's twice as big or 3 times as big. But when you actually move it down here, then this guy is like immediately looks like so tiny compared to the other guy. Even in the image plane, like this kind of looks bigger than this to me. Because we implicitly, like internally, just undo that distortion, and we tend to view things in terms of their real size according to the scene context instead of their image plane size. So small changes to context can change our perspective. So here you can see there's like a small guy in the front, and then the guy is getting bigger as you go back, right? And then if I change the lines, now they're all the same size. And then if I do this, now they're all the same size, but of course, like the guy in the back is getting smaller in the image plane. Right? And this is actually, this construction with lines is a basic way that we can solve for image sizes. If we have a line going through the guy's foot and a line going through the top of the guy's hand, and those lines intersect on the horizon, then we can say that, and we know those lines are parallel, then we can say that that they're all the same height, like that the line, any objects where these lines pass through are the same height. So these there's a lot of it's possible to even make like physical illusions that take advantage of these constraints. So this is a time-lapse image where it's a combination of 2 images, where it's the same person in 2 parts of this room. So they do this by, it looks like the person on the right is a giant and the person on the left is much smaller. because you assume that the clock is a circle and that there's a grid pattern on the floor and that the windows are rectangular and that the wall structure is rectangular. But actually, none of those things are true. Like, everything is carefully constructed so that when you look at it from the right position, it all looks like it's a normal room, but in fact, it's a weirdly constructed room where you actually have like the floor sloping downward here, or upward here, so that when somebody is standing back here, it looks like they're standing much closer. And when somebody is, and then the person standing over here is actually much closer, so they're larger. So you end up making it look like there's a small person standing closer because these two people are at the same height in the visual field, but one is just at that height because, actually, the floor is sloped downward, I should say. Because when the floor is sloped downward, it counteracts that as you move further away, you go higher in the visual field. And then all of these lines are constructed so that it all looks like rectangular. All right, so let's look at how we, in a normal world, normal scenes, how we can compare the heights of objects. So we can do it with our vanishing points and vanishing lines. So the way that we do it is by, if we've got all these people and we want to measure the relative size, then we can construct a line through their base that's on the ground. So we're just going to say, by construction, this line is on the ground. And then we generate another line from the intersection of that ground line with the horizon, which is the vanishing line of the ground plane, through the top of one of the other person's hands. And then that gives us their relative height. So in this case, they're all the same height. So the important thing is that I generate a baseline that I'm going to say is on the ground. Then if I have another line that's parallel to that baseline and also parallel to the ground, I know it has to come from this vanishing point. And so if it passes through some point on the object, then it must also pass through that point on the object in the image plane. And so I can construct another line. These lines are parallel in 3D, so I can measure relative heights from them. So here's another illustration. Let's say I have a big ruler in the scene. If I want to measure how tall is this person compared to the ruler, then I draw a line from the base of the ruler through the base of the person and look at where it intersects with the vanishing line of the ground. Then I take that intersection point and I say this is going to be my vanishing point of a pair of parallel lines. So I draw a line from that point through the top of the guy's hand and look at where it intersects with the ruler. And now I know that the height of the ruler is the same as the height from this guy's foot to the top of his hand. So in this illustration, the man is like 5'5" or something. Well, his hand is 5.3, I said there. Well, 5'5", not 5.3. 5.3, whatever. Okay, so so if we wanted to then measure the turtle, we draw another line through the base of the turtle from the base of the ruler, see where it intersects with the vanishing line, and then draw through the top of the turtle, and then we get a different measurement. So what's the height of the camera in this scene? Yeah. So if I were to draw a plane that's parallel to the ground through the camera center, what would that image look like? What would the image of that plane look like?
It would be a line. That's the horizontal line that we're seeing at the end.
Yeah. So if I drew a plane parallel to that's parallel to the ground through the camera center, then it's also going to intersect on the vanishing line. And it's just going to be, in fact, since it's through the camera center, it's just going to be, the image of it will just be the vanishing line. And so what's the height of the camera? Yeah, so there's some muttering in the generally right direction. So 3 point, a little under 3.5. So it's just so the line, that plane imaged onto the camera would just be this red line here. And so the place where that line passes through the ruler is the height of the camera. So this gives us a kind of neat trick that we can measure the, we can say, for example, in this photo where we can see the horizon really well, that the camera is higher than the man and lower than the parachute. Because if we project a line through the horizon, I mean, if we had a plane that's parallel to the ground, it would project along the horizon, so the camera's height is, about right here. There's actually as you get really high up, there's actually a significant factor due to the curvature of the Earth, but still the horizon as a plane is probably like about right here. Question?
At this very same height, if I tilt the camera downwards, the horizon will go up, right?
Yes.
So how's that working?
So it still works, but I always have trouble explaining, re-figuring out. Every time I think about it, I have to re-prove it to myself that it works. And right now, I just remember that it works.
What is the question again?
Oh, sorry. So the question was, if the camera tilts, then the horizon moves. So does this property still hold that that all the objects that the horizon passes through are at the height of the camera? And it still does work. There's a yes. That's right. So what will happen is if I tilt down any object that's currently above the horizon will move as well, and they'll still be above the horizon. And any object that's below the horizon will move down, and they're still below the horizon. But there's, I have some illustration for this, just not right here, that kind of helps to show why it doesn't depend on the camera tilt. So that's actually, I've used that a lot just to make casual measurements of things. So as a result, you can also, if you know your height, you can measure lots of things. If you know the height of also if you know the height of different parts of you, you can basically be the ruler in that scene. Sounds more grand than, depending on how you interpret that. So one thing that we haven't dealt with these vanishing points is that these measurements here assume that we have a vertical vanishing point at infinity, because it assumes that that this length is that the lengths in the image in the vertical direction are proportional to the lengths in 3D. And that's only true if the vertical vanishing point is at infinity. In other words, if our camera is perpendicular to gravity. If not, we have to use this one invariant that we get, this one projective invariant, which is really difficult to say. But it's basically that the ratio between, I can't say it, if you have the cross ratio of 4 collinear points is the simple way to say it. But what it says is that if I've got the ratio of, let's say, I'm going to compute the distance to these 2 points, P1 and P2, from these other 2 points, P1, P3, and P4. So the ratio of P3 to this distance between P3 and P1 over the distance between P3 and P4 times that inverse ratio, so the distance of P4 to P2 over P4 to P1 is always constant. It's constant under projection. So that cross ratio is the same in 3D as it is in 2D, no matter what my points are, and no matter what my rotation and translation and intrinsic matrix is, and et cetera. Because it's all a perspective projection. So this is called the fundamental invariant of projective geometry. So we can actually use that, maybe surprisingly. So now if we want to measure height, what's going on is that we've got some object in the world that's vertical, we'll assume. And so now we've got some reference point and some top of the object, and let's say we know h, and we want to solve for the reference point. But now we're going to assume that the camera is at a slant. So the camera is at a slant. And so now we've got foreshortening, that we can't just measure the lengths in 2D and have the ratio be preserved in 3D. Or the 3D ratios are not preserved when we project onto 2D. But now if we image all these points, we've got the vanishing point in the z direction, the projection onto, and then the 2D coordinates of the reference point and the top of the object. And we'll assume that we know all these points. So we've solved for the vertical vanishing point. Then we've got this scene cross ratio is equal to h over r. So the distance between the bottom and the top over the bottom and r times the inverse ratio between this other point, which is at infinity, is just equal to h over r. And then in 2D, the ratio is the bottom minus the top over bottom minus r times the inverse ratio of the 2D of the vanishing point, which now is finite because the camera is tilted, minus the r over vanishing point minus the top is also equal to h over r. Because I have this projective invariant. Because these 3D distances in the cross ratio are equal to these 2D distances. And note that if the vanishing point were also at infinity, like in the other examples, then I would get the previous relationship where the 2D relationship is preserved. The 2D ratio is the same as the 3D ratio. But if your camera is tilted, then only the cross ratio is preserved, not the ratio. So here's an example. So now let's say the camera is tilted. So note how I'm assuming that this column is actually a cylinder, but note how the lines are warping in because the camera is tilted slightly up. Then I think that's right. Well, the camera's tilted. Then the vanishing point is some finite value up here. All right. So what do we do? So what's the first line that we draw? If we want to measure, let's say that we want to just measure how tall the person is compared to the column. We know the column's like 10 feet, for example, and now we want to measure the person. So what line do we draw first? What? Yeah, the baseline. The line. So we draw a line first through B and B naught. And so here I've drawn vanishing point x and vanishing point y, but those are not related to this measurement. Those are just happen to be where those other lines are intersecting. And actually, it's important not to be confused between the vanishing points of the scene and the baseline that you're drawing to try to measure the positions of these objects. So this is a different direction, a slightly different direction than the x direction. Now I need to draw a line from the V through T naught. So I can draw that first baseline. So I draw from V to T naught, and that gives me H. And then I can use the cross ratio of these 2D distances between VZ and R and VZ and T, and between T and R to measure the 3D ratio between H and R. And then if I know either H or R, I can compute the other one. So just as a note, you can compute these equations pretty simply using cross products if you're representing your points and lines in homogeneous coordinates. So the point V is just B cross B naught cross Vx cross Vy, because B cross B naught gives you B cross B naught gives you a line through B and B naught. So if you do B cross B naught and then cross that with Vx and Vy, then it gives you that intersection point V. Then if you want to try to find T, it's the intersection of the line from V through T naught with the line through B and R. So you do V cross T naught cross V cross R. B cross R, I meant to say. Right? So when you take the cross product of 2 points in homogeneous coordinates, you get the line through them. And then when you take the cross product of 2 lines, you get the intersection of those lines. So it makes it really easy to compute these values. If you just had stored in your program these 2D positions, then you can compute everything in a few lines of code. All right, so here's a tricky one. So now let's say that there's a guy standing on a box, and we don't know where, we don't know the height of the box or the height of the man, but we want to know the height of the man. So, and I do know the height of the pillar. So how do I solve this? So first, what is the most important thing for me to figure out in order to solve this? Yeah, well, actually, guess maybe the height of the box could help, but even if I knew the height of the box, I wouldn't really be able to do it by itself.
On the point on the bottom of the box where the man is hanging, the base point of that.
Yes, that's right. So it was that you need to find, we want to figure out where the guy is standing above the ground, because only if we know that point can we make a vertical line through the guy. And so then we can see, if we know the height of the box, then we can measure the height of the guy compared to the box. And, or we can construct lines through the base of the man on the ground with the base of the pillar. So how do we get that line? So we can do, so we can use the corners of the box. We know that the front corner of the box is on the ground, and the top corner of the box has the same height as the man's foot. So we can construct a line from the top corner through the guy's foot. We know that's parallel to the ground. Then we construct a line that's parallel to that, which has to come from that vanishing point through the front corner of the box, because we know that, and we know that B1 is under B2, so directly. So we also know that if we pass a line through the guy's head through his foot and intersect it with that line, then we get the point in the scene that the guy is directly standing over. And so now we can use the previous methods just to solve for the height of the man or the height of the box. So we can, for example, we can go B through B naught and then through T naught to get the height of the man plus the box, and then go through B naught and then back through M naught to get the height of the box, and then we have everything. Okay, so now I want to talk about some of the other camera parameters that some of them either do not purely have to do with perspective geometry, or they have other, basically these parameters all have effects on the image, even though they don't really affect the way that we talk about projective geometry. So focus, for example, there's terms like when you zoom, the focus affects how blurry the image is when parts of the scene are out of focus. The aperture affects how much light comes through and also affects how blurry things are. The depth of field affects how blurry things are as you get out of focus. And the field of view is measuring how much of the scene you're viewing at some time. So let's get into that. So the reason why a lot of these things come into play is that we don't have an ideal system. So we don't have this ideal pinhole model where we've got an infinitely small pinhole and lines are projecting from the light is projecting and rays from the scene through this infinitely small hole and hitting the image plane at exactly one point. Instead, in order to get more light in there, we have an aperture. So the pinhole has some size to it. It's not infinitesimal. And the lens is focusing the light onto the film through that hole. So as a result, there's some specific distance due to the lens at which objects are in focus. And so in this illustration, the red point is in focus. So the lens will focus everything onto the film at exactly the same point. But the purple point is not in focus. And so the lens focuses it over some area of the film. And that's called the circle of confusion. So it's going to be, it determines how blurry that point will be. Because instead of all the light focusing onto one pixel, it's focusing onto some small set of nearby pixels. So here's our model with the lens. And this one is also kind of an important illustration to remember. We've got now instead of an infinitesimal pinhole, we've got an aperture of diameter d. The focal length is the distance of the lens to the focal point. And I guess that's it. And then, so the image plane is back where the focal point is. So, so the reason why one reason that you still want a smaller aperture is because if points are out of focus, then if a point in the scene is out of focus, then the further away you get from the center, the further away its projection will be on the image plane from a line that passes through the center. So increasing the aperture will increase the amount of blurriness of far points while letting more light come in. They'll increase the blurriness of points that are far from the focal plane in the scene, I mean. So this model of the camera is actually remarkably, well, not coincidentally, but extremely similar to the model to our eye. So with our eye, we've got a lens. So light comes in, it goes through some lens, and then it gets, the iris is the muscle that controls our aperture. So we can change our aperture, we can change our focal length, and then the light comes through the lens, and it's projected onto this, you could think of it as a retinal map, all the cones and rods that are in the back of our eye. Then that senses everything, and then it goes through an optic nerve, and then we process it. Right, so the analogy is that the iris is our kind of like our shutter. It's affecting our pupil size, or I mean, it's affecting our it's affecting our pupil size. Our pupil is the aperture, so that dark part of your eye is where the light's coming in. And then the retina is like the film. So the retina is the photoreceptor rods. So that's why if you're looking at bright light, your pupil will get very small because you don't need as much light to get in, and you don't want it to, so you don't overwhelm your cells. And if you're in a dark room, then your pupil will be much larger, so you let more light in, because that's your aperture. So now that we've got a lens, now we get some complexity to how the image is formed. So all of our geometry is still fine in terms of where a scene point projects, or the center of where it projects anyway. But now a point that's out of focus doesn't necessarily project to a single pixel. The light coming from it, because there are different angles of rays that will hit the lens, if it's out of focus, then they'll project onto a range of points on the sensor. So if we have, if the aperture, the depth of field is a term that indicates how far can things be out of focus, how far can things be away from the plane of focus before they get to some blurriness level, or before the circle of confusion is greater than some number. So if the aperture is really big, then you have a small depth of field. So here the flower is in focus, but the things behind it are all completely out of focus. If you have a small aperture, then you have a large depth of field, and so the objects around the flower are more in focus. They're just a little bit blurry. And so that's why you often get, you do in your camera, you might have like an F number for the aperture, which is, you think about it in terms of the ratio of the focal length, so that you're thinking of it in terms of depth of field and like how much things are in focus. rather than just in terms of the size of the aperture by itself, because the focal length and the depth and the aperture size interact to create the depth of field.
Where are you making these dotted lines? How are you making these dotted lines?
How what?
How are you making these dotted lines?
Well, it's just an illustration, but it's showing that it's meant to show that that the dotted lines are, that's like the extent of the depth of field. So in this illustration, points that are within this for the large aperture will project down to within some, say, like 3 pixel radius. And points that are within this with the smaller aperture will also project down to some 3 pixel radius. And it's because when you have a smaller aperture, there's a smaller range of angles that enter the lens. When you have a larger aperture, there's a larger range of angles coming from the object that enter the lens. So here's another illustration. So we've got, on the left side, large aperture, small depth of field. You can see that like the cherries in the back are blurry. On the right side is a small aperture, and you get a large depth of field. Everything is more in focus. So one thing you might ask is, like, why not, or I could ask, I guess, why not make the aperture as small as possible? So what happens, so here we can see that as this back plane is out of focus, but as I make the aperture smaller, it gets sharper. So what prevents us from making everything in focus just by getting back to our pinpoint, by having like a extremely small aperture? Yeah, so one problem is that we won't get enough light. And another problem is that you can get diffraction effects. So you might remember from physics, if you pass light through a very small slit, then it actually diffracts the light, that the light will bend. And so so if you make it too small, you actually can get a more blurry image that's also noisy, because now you've got effects due to diffraction, and you've got noise in your measurement because not enough light is getting through. So another term that's important is the field of view. So the field of view is just the angle at which you can see in your image. And this is related to the focal length and the sensor size by a simple geometric formula. So here we've got so the field of view will be determined by what range of points what is the range of angles at which I can see points in the scene, and the rays from those points will pass through the center of my lens and still hit the sensor. So if I have a point out here and it goes through the center of the lens, it won't hit the sensor, so I won't see it. And the same out here. But for any points in here, it will hit the sensor array in this like overhead like 2D view. So, so you can just do the simple geometry to figure out that the tangent of the field of view, so the tangent of half the field of view is equal to d over f, opposite over adjacent. This is f, this is d. So the tangent of this angle is equal to 1/2 d over f. And so then the inverse tangent of 1/2 d over f is equal to the field of view. Actually, it's the half field of, this is, should be 2 times inverse tangent d over 2f is equal to the full field of view. The inverse tangent of d over 2f is equal to this angle, whatever that is, phi, I guess. I don't know. I'm bad at Greek letters. So, so you can actually, I think okay, so I'm going to skip this. You can look at this later, though. You can actually create interesting effects by zooming in while you're moving back, and so that you keep an object the same size while everything around it is changing in its size and in its focus. So just bear with me for 2 more minutes, because I want to just say how we can answer these questions as a summary. So now how do we answer these questions about how tall is the woman, how high is the camera, what's the camera rotation, what's the focal length, which ball is closer? Okay, so first, the first thing we'd want to do is construct vanishing points. So we can measure the 3 vanishing points based on the orientation of this pitch. So we've got a couple of walls there that we can use, and the tops of the walls to find a vanishing line in the longitudinal direction. We can use like the lines on the fence here on the right side to find the vertical vanishing point. And then we can use these parallel lines on the back of this pitch or whatever it is to find the horizontal vanishing point, for example. And there's also some fences and stuff that we could assume are horizontal. So once we've got 3 vanishing points, then we can solve for the rotation of the camera, and we can solve for the focal length of the camera. And also from 2 of those vanishing points, which are parallel to the ground, we get the horizon. So if we know, this is a game where you have standardized sizes for the balls. The standard size of a bocce ball, which I looked up, is 107 millimeters. So once you know if you know the size of the ball, then by constructing the ratio, you can construct lines through like the bottom of the ball and the person's feet, for example, and the top of the ball through the woman's leg, and intersecting those with the vanishing line to calculate the height of the woman compared to the height of the ball. Then if you know the height of the ball is 107 millimeters, then you can calculate the height of the person. Once you know the height of the person, based on where the horizon passes through the person, then you can calculate the height of the camera. Since we can solve for the rotation and the focal length of the camera based on these 3 orthogonal vanishing points, then we have and we know the height of the camera, then we have a t, we know the y component of the translation vector from the height of the camera, and we know r and k. And so we can just write down a system of equations, or just a set of equations to solve for the 2D points of each of these things on the ground. Because these are at y equals 0, and the camera is at some known height. And so now we have 2 unknowns, which are the x and z values, and 2 knowns, which are the u and v values. So we can solve for the 3D positions of each of these balls, and then we can answer which one is closer. So we can get all of this basically just from the vanishing points and by constructing some lines. All right, so that's a review of the last 2 classes. And then in the next class, I'm going to talk about image stitching, which is how we can start to combine multiple images, in this case to create a single canvas on which we paint all of their pixels. Thanks for waiting. Have a good week. What day is it? Thursday? Have a good weekend.